Hello everyone, my name is Tianchi Sun. The paper that I will present today is named as the Improved Optically Self-Injection Locking Phase Locking Based Forced Oscillator using Fiber Laser. My co-author, Professor Afshin Darush, coming from Drexel University, and our collaborator are Dr. Li Zhang, Dr. A.J. Porter, and Professor Rudy from Synergy Microwave Corporation. And this is my presentation outline. We will first introduce the demands for the low noise oscillators. There are many different fields reaching great demands for the low phase noise oscillators. For example, in stable clock signal in coherent detection system that's used for sample and hold analog to digital converter. Second is the high-speed telecommunication and high-resolution sensing using for wireless base station, radar ranging and remote sensing, as well as the space communication field. We need to use it for satellite, international space station, and Mars rover. After talk about the great demands for the low phase noise oscillator, we will review the background in forced oscillation techniques. There are conventional injection locking and the conventional phase locking loop, which need an external reference to stabilize the output from the voltage control oscillator. This is a conventional design. We need an external reference, and the performance depends on the external reference spectral purity. In our experiment setup, we're using the self-injection locking and the self-phase locking loop, which can use the output from the voltage control oscillator itself, then suffer from a delay created by an optical fiber to create that reference for the oscillator itself. So in our design, the better spectral purity can be achieved if we're using the longer delay lines of that is optical fiber, and the performance is no longer limited by the external reference. This system series is first published by the group of Professor Afshin Darush in 1993 using the injection locking and phase locking loop, and Dr. Li Zhang how to use. Dr. Li Zhang further developed it into the self-injection locking with self-phase locking combination system. So in his design, he used the DFB laser with the electro absorption modulator, which has the not very good relative intensity noise performance. So this is the modeling self-injection locking phase locking theory that Dr. Li Zhang raised in his paper. In this theory, the loop transfer function is represented by the HS here, which is using the gain of the loop gain over 1 plus the gain. The gain consists of 3 parts. One is the voltage control oscillator turning efficiency. The second part is the mixture convention efficiency. And the last part, F, is the filter transfer function. So the overall phase noise performance will be expressed in the equation below. From this part, the first term is the contribution through the delay optical fiber lines, which is in our self-injection locking phase locking loop created by the optical fiber to function as the delay. The last term is the oscillator noise itself. So when the gain is high enough, the HS is very close to the unity, so the contribution through the oscillator itself will become very, very small. So the system will depends on the delay lines that we created. The third part, we will talk about the realization of the dielectrical resonator oscillator and the optical electron oscillator based forced oscillator using different laser source. The laser source we are using here to make comparison, the first is the DFB laser, which has the relative intensity noise only negative 120 dB per hertz. That is used in Dr. Li Zhang's paper, but in our paper we're using the more advanced fiber laser, which has negative 157 dB per hertz relative intensity noise. And the line width is also very narrow in fiber laser, which is 10 kilohertz instantaneously, which contribute to PM to PM noise conversion. When compared with the DFB laser, it has 10 megahertz line width And the fiber laser source also has very high output power, so we can get rid of the EDFA when compared with the DFB laser system and the FC-UFFC connector using in fiber laser experiment setup can save one polarization controller. This is our experiment setup for the block diagram, and the top left is the block diagram, and the below right is our system realization on optical table. This is our block diagram. We use the laser source, which is a fiber laser, to introduce the light to the dual drive Mach-Zehnder modulator. Then we go through the EDFA with a 50-50% coupler, divided the light into two different paths. One goes through the 3 kilometers optical fiber to function as the injection locking. Another shell with the 5 kilometers with 3 kilometers to function as the phase locking. The signal will go through the amplifier to do the phase locking, but for injection locking, the power is high enough. We don't need any amplifier, so the amplifier performance has been, the effects of the amplifier performance has been reduced. After we combine the signal at amplifier and output to the mixer, we detect the phase arrows with the DRO output, then output the phase arrow to the DRO to do the phase locking. The phase locking the DRO signal output will go through a dual drive, a push-pull amplifier, which created a 180 out of phase, but keep the same amplitude. So in this design, we can drive the MZM in the dual drive model, so we can lower the noise figure level of the optical link. And this is our experiment realization in our lab. The part is the fiber. After the fiber, when the signal is combined photodetector, and we go through the amplifier with the mixer. We use go to the mixer. Then we export the phase arrow to the DRO, dielectrical resonator, which is a commercially available one from Synergy Corporation. We use this system to lower the phase noise performance, and the push-pull amplifier is at the output of the DRO. We use this to generate 180 out of phase signal to drive dual Mach-Zehnder modulator. This is our experiment result compared with simulation result using DFB laser as well as fiber laser. In our simulation, the experiment, this is for self-injection locking, only using the 4 kilometers long fiber. We see the performance match with the between simulation and the measurement, and we even overcome the problem we meet at the plateau that appears before beginning around 10 kilohertz offset frequency, and now we can keep the phase noise performance keep decreasing until 20 kilohertz offset frequency. And this is the combination for self-injection locking with self-phase locking. The self-phase locking contributes most of the phase noise decrease in closing carry frequency, and self-injection locking charge of the far to the close to the carry frequency. So we decided to combine them together in order to achieve the better performance. After using the combination of self-injection locking with self-phase locking, we use the dual phase locking in order to get rid of the side mode peak. The side mode peak will appear periodically according to the phase locking loop delay optical fiber that we are using. So we're using different lengths for the optical fiber to use for the phase locking loop. The side mode peak will appear at different positions so they can compensate each other. This is the performance comparison that we have in tabular form. The free running DRO at offset frequency of 1 kilohertz, it is negative 83.2 dBc per hertz, and using the self-injection locking with the DFB laser, it can reduce to negative 97.3 dBc per hertz. Using the fiber laser, it can go even lower than negative 102.3 dBc per hertz. For self-injection locking, self-phase locking combination, the DRO using the laser, using the DFB laser can reach at negative 100 102.3 dBc per hertz, while for the DRO, using the fiber laser, we can reduce to negative 106.3 dBc per hertz. You see on in the last row, we use the dual self-phase locking. The performance is almost same for the self-phase locking, but actually we get rid of some side mode peak, which we'll show in next slides. For the OEO performance comparison, we use the free-running OEO with self-injection and self-injection self-phase and self-injection locking, dual-phase locking. I only show the performance comparison here because of the space limitation. This is the side mode summary on the side mode peak separation. We're using the DFB laser with fiber laser in the single self-phase locking loop. We will observe two spurs position, which one is appear at 45.23 kilohertz and the level is at negative 83 dBc. Another is appear at 86.53 kilohertz and the level as negative 94.3. That is for the single phase locking loop. When we move to the dual self-phase locking loop, we can get rid of one side mode peak and we only have one. And we even do the experiment using the triple loop, so that no high power spurs will appear anymore. So this slide just explain the reason why we use the dual loop and the triple loop for the phase locking. And this is the next part. We will talk about the phase noise limitation and the latest result we get using the optimized system. Actually, the limitation in our system has two parts. The first part is the relative intensity noise. We have already lowered from negative 120 dB per hertz to negative 157 dB per hertz when compared with Octalijan's paper. And in our setup, the limitation through the calculation, when we reach the optical power, optical current, when we reach the current as 10 milliamp, the lowest phase noise we can reach is negative 136 dBc per hertz according to calculation. But if we can even further lower the relative intensity noise of the laser source, for example, we reach at negative 170 dB per hertz, we can expect negative 147 dBc per hertz as the lowest phase noise when other components keeping the same in the system. The second part is from the amplifier. In our system, the amplifier flicker frequency is negative 80 dB rad per square, and this is our simulation result with the experiment result. I even did the simulation result using a better amplifier. The flicker frequency reached at negative 90 dB rad square. When we use this amplifier, the phase noise performance can be even reduced. We can reach negative 137 dBc per hertz. And from the state of art of the amplifier design, the lowest flicker frequency that we know now is reported as negative 130 dB rad square. So we can further reduce our phase noise performance. This is our conclusion. The measured phase noise performance follows the analytical prediction of self-injection locking, phase locking model, and low ring noise of the fiber laser system, resulting in a 3 dB and 6 dB phase noise reduction at offset frequency 1 kilohertz and 10 when compared with the large ring DFB laser. A lower flicker noise amplifier of negative 95 dB rad square will result in a negative 140 dB per hertz phase noise for a 10 dBm forced oscillator. And the last part is talk about the contribution of our system, the flicker frequency of IF amplifier. If we can get a better one, we can reduce the phase noise. Second is the ring noise of the optical source. The third is the optical source line width, which contribute to PM to PM conversion. When we can further reduce these three parameters, we can achieve the better performance. Thank you for your attention. Any question? I think I have a problem to using this.